Welcome to Chapter 4.1, Events and the Sample Space. In this section, we begin building the foundation for probability, one of the most useful and widely applicable parts of statistics. Whether you're analyzing quality control at a factory, forecasting business risk, or modeling customer behavior, probability starts with understanding the possible outcomes of an experiment. Let's break this down step by step. In statistics, an experiment isn't necessarily a lab experiment. It simply means any process or action that leads to an observable outcome. This could be tossing a die, choosing a student at random and recording their major, or tracking whether a customer clicks on an ad. Every time we carry out an experiment, we are interested in what outcome we get, and that's what makes up the basis of probability. A simple event is just one specific result from an experiment. If you roll a six-sided die and get a 4, that outcome is called a simple event. We might label it as a capital E subscript of 4, meaning the event where we observed a 4. Each possible individual outcome is considered a simple event. In real-world terms, if we check whether a customer made a purchase or not, then the simple events might be purchase and no purchase. If we ask for a person's blood type, then each of the blood types, A, B, AB, and O, are the simple events. These are the building blocks of the sample space. So the sample space, which we label with the capital letter S, is simply the set of all possible simple events. If we roll one six-sided die, then the sample space is capital S equals 1, 2, 3, 4, 5, 6. In the curly brackets, these curly brackets indicate that it is a set. Every outcome that could possibly occur is listed here. Let's take a different example. Suppose a business is launching a new product and tracks the response from 100 emails. The sample space might be S equals click or no click on the email. Again, in curly brackets, indicating that it is a set. Or even more detailed, right? Maybe the sample space is open and click. Open and no click. And not opened. Curly bracket, right? What matters is that the sample space covers all of the possibilities. Now that we understand simple events and the sample space, we can define an event. An event is just a set of one or more outcomes. So when we say event A is rolling an odd number, we're including several simple events in that one event, namely 1, 3, and 5. Similarly, the event roll less than 4 would include 1, 2, and 3. A statement like less than is exclusively less than, right? So it does not include the 4. This is really helpful in business and health contexts. For instance, a health study might define an event as patients with high cholesterol, which could include multiple ranges of lab results. In all cases, an event groups outcomes into a meaningful category. Two events are said to be mutually exclusive if they cannot happen at the same time. Think of it like a fork in the road. You can go one way or the other, but not both, not at the same time. For example, when rolling a single die, the events even number and odd number are mutually exclusive. No roll could be both of those things at the same time. But let's go back to our earlier example. We had event A, lost my pen. Okay, we had event A as 1, 3, and 5, rolling an odd number, and event B as 1, 2, and 3, rolling a number less than 4. These are not mutually exclusive because they share outcomes. Specifically, 1 is in both sets and 3 is in both sets. So it's possible to roll a number that satisfies both A and B. Knowing whether events overlap helps us calculate probabilities correctly. Now, I'm really not sure why AI thinks that a cup of tea and a campfire are mutually exclusive events that a capybara could be holding, but we're just going to roll with that. Venn diagrams are an excellent way to visualize how events interact. In this example, we draw two circles, one for event A, the 1, 3, 5, and one for event B, the 1, 2, 3. The overlap, this thing, includes the outcomes 1 and 3, where they overlap. These are the outcomes that belong to both events, and they go in the center in both circles. Now, that symbol that we see right here that looks like an upside down U, that is the mathematical symbol for the word and, or the intersection. We'll explain more about that in an upcoming lesson, but it just means what A and B have in common. This kind of diagram makes it easier to answer questions like, what's the probability of A or B? Or what's the probability of both A and B? Especially for students who think visually, this tool can make the abstract much more concrete. When an experiment involves more than one stage, a tree diagram can help us map out all possible outcomes. In this example, we have two stages, blood type and Rh factor. The first branch shows the 4 major blood types, A, B, AB, and O. From each of those branches, we add 2 more, a plus and a minus, representing the Rh factor. This produces a total sample space of 8 outcomes, A positive, A negative, B positive, B negative, AB positive, AB negative, O positive, and O negative. Tree diagrams are especially useful when calculating compound probabilities, such as the chance that a randomly selected person has type O negative blood. Let's apply what we've learned. Imagine a capybara technician inspects a product randomly selected from a shipment. The product is either working, capital W, or defective, capital D. And it either came from plant A or plant B. All right, first out, let's list out the sample space. So our sample space, S, would be working from A, working from B, defective from A, and defective from B. Those are all our possible outcomes. Next, let's define the event working. All right, so W equals, well, it could be working from A or working from B. And let's define the event from plant B. So from plant B would be working from B or defective from B? That's a B. Okay, now ask, are the events working and from plant B mutually exclusive? No, they've got something in common. The outcome, W subscript B, belongs to both of them. This type of reasoning is foundational in business analytics, where you're constantly evaluating product reliability, source quality, and error rates. So to wrap up, an experiment is a process that leads to an outcome. A simple event is one specific result. A general event includes one or more such outcomes. The sample space includes all possible simple events. Some events are mutually exclusive, while others can overlap. Venn diagrams and tree diagrams help us organize and visualize these ideas, especially when problems grow more complex. Understanding these basic building blocks sets the stage for everything we do with probability, from estimating risk to designing simulations to interpreting data in the real world.